Our last topic for the heat part of Sci 8511 is change of phase, and this will take us right into the reading week. So we know that matter can exist in phases like solid, liquid, gas, and we know that matter can change phases from solid to liquid or back, from liquid to gas or back, and then you can kind of skip phases too, but you'll notice I've capitalized a couple of words because we are going to define a new variable, two new variables that use these terms. So when you think of fusion, you are thinking solid to liquid or back again, and you're thinking of vaporization, liquid to gas or back again. Even though there are other words, just remember fusion and vaporization, and that's what they refer to, because we know how to calculate the heat in a phase. We use a Cm delta T formula, but we don't yet know how to find the heat absorbed or released when we are changing phase, and we'll need to figure that out. So here we just have a little thing that explains everything. I've added fusion here, vaporization is here, and I'm going to use vaporization to talk about all things when you're switching from liquid to gas or gas to liquid, and fusion to talk about when we're switching from solid to liquid or liquid to solid. A big part of calculating phase change is going to be using graphs. So things to notice here. I have drawn a graph, which is just me drawing a y-axis, a vertical axis, and a horizontal axis. And you'll notice I'm putting temperature on the vertical axis, and I'm putting heat on the horizontal axis. So when we draw these, it'll always be like that. So this slide is titled temperature change during, or temperature during phase change, and this is the important one. So you can see that, let's say this is for water, so I can label some temperatures. I know that I change from solid to liquid at 0 degrees Celsius, and I change from liquid to gas at 100 degrees Celsius. So I'm just using Celsius because it's what I know. We will calculate in both metric and imperial. So let's look or follow along with the temperature. So I start at some temperature, let's call it minus 20, and I'm looking at what's happening on the vertical axis. So I warm up this ice, I warm it up, I warm it up, I warm it up, and at point B, we're going to start creating water and losing ice. But notice what's happening to the temperature. So if it's a horizontal line, we're not increasing the temperature because the temperature change from point A to B is here. But the temperature change from B to C, it's a flat line. It doesn't leave 0 degrees Celsius. So between B and C, there is no change in temperature. However, something is still happening with the heat. So at point B, we have ice at 0 degrees Celsius. At point C, we have 100% water at 0 degrees Celsius. So while you are changing phase, the temperature stays constant, and it will only resume increasing once you have changed all of the ice to water. So if there's a little bit of ice left, the water is going to stay 0. All right, what happens next? We raise 100 degrees Celsius and we get to point D. At point D, we have water at 100 degrees Celsius. And at point E, we have, steam at 100 degrees Celsius. So at point D, 100% water. In between D and E, some combination of both. Point E, 100% steam. So if you're boiling a pot of water, it's going to stay at 100 degrees Celsius until you get rid of all that water, which is a weird concept, but the temperature does not change during phase changes. We're going to turn our attention to the horizontal axis now. We're looking at the heat. It's always increasing. So if we think of between point A and B, which was from, some low, let's call it minus 20 degrees Celsius, just guesstimating, but we know that B is definitely 0 because we see a phase change happening there. So if we think here, we have heat, we're adding heat to that system. The heat is increasing. But whereas between B and C on the temperature axis, nothing was happening, we're still adding heat between B and C. So you're always adding heat. Or if you're going down from gas to solid, you're always taking away heat. Heat is always increasing or decreasing when you're doing these kind of phase change calculations. The problem is between B and C, our formula is Q equals Cm delta T. So if I wanted to use my traditional, specific heat formula to find the heat absorbed from B to C, I would start C whatever it is, M whatever it is. If I'm thinking about delta T, the temperature at C is 0. The temperature at B is 0. Or if I was at vaporization, the temperature at E is 100. The temperature at D is 100. So these both create situations where you're multiplying Cm times 0, which is going to tell you that there is no heat absorbed between these 2 points, and that's not true. So we need a new formula. And just to make it confusing, we're going to have 2 different formulas, or we're going to use 2 different variables depending on whether our phase change is between solid and liquid, or our phase change is between liquid and gas, either way. Okay, so new variable, heat of fusion. So when we're dealing with solid and liquid and changing back and forth between that, we use the variable heat of fusion. It is a big L with a subscript F, F for fusion, L for latent. And latent means hidden. So why is this a hidden heat? Because you can't see it. From the temperature remaining constant, you would assume that the heat is not increasing, but it is. So it's like a hidden heat. All right, so the key thing I need you to remember, when do you use a heat of fusion, which is, got a variable, remember that, which is LF, is that you use it when you are changing phase between liquid and solid. And that's the only time you're going to use it in this phase change calculation. Let's bring it into the formula. So what it is, a heat of fusion, technically it's the amount of heat that you need to change phase of 1 gram or 1 kilogram or 1 pound of solid or liquid there and back. So the formula is easy. This time we're going to find heat by multiplying 2 things, the mass or the weight, depending metric or imperial, same, of the substance that you have by the heat of fusion, LF. Okay. Variables are listed down here. You will look to your formula sheet to know which units to use. And let's take a look at where this is on your formula sheet. Here it is. So this is the same one we used for a specific heat. We were looking here. So when we're in a phase, we're using Q equals Cm delta T. And when we are changing between liquid and solid, we use Q equals LFM. And you'll see some are listed here. I don't have them for everything because we're not going to be changing phases of metals other than mercury, but it's a weird one. But I have it for ethyl alcohol. What's interesting here, we have one for ice because ice is the solid form of water. It's the same as the one you see down for water. And I don't have one for steam because steam has nothing to do with heat of fusion. It uses the next thing we're going to talk about, heat of vaporization. Noticing that you can get the units by looking at what's going on up top. So if you want to calculate your heat in calories, your mass is in grams. You want to calculate your heat in calories, your mass is in kilograms. Or you can do joules in kilograms, although those numbers are always huge because you can tell they're huge because look at the scientific notation in that column. And then if you are using pounds as an input, you're going to get BTUs as an output. We'll do a couple of quick examples of how to calculate heat flow from the heat of fusion. So I'm just going to draw it quickly. Again, I have temperature and I have heat. Where are we in both of these questions? We're at this first flat area. Okay. How much heat must be released to turn 2.5 pounds of water to ice? So we have pounds going in. I know I'm going to get BTU out. So I go Q equals heat of fusion. Whoa, that's F. I need an L in front of it. There we go. LF M or W. I'm just going to use M because that's what I always say. And we're going to have Q equals, and we need to go find out what LF is for BTU for ice or water. So I'm going to go back to this, and I see that if I'm looking at ice or water, they both give me the same value in the BTU column, 144 BTU per pound. So that goes in for LF, heat of fusion, and 2.5 goes in for the pounds, and all you're going to get is 360 BTUs. So that means, first of all, the difference between here and here is 360 BTU, and it means that in order to change ice to water or back, you either have to add 360 BTU. If you're talking about 2.5 pounds, it'd be different if it was a different mass or weight. You're going to have to either add 360 BTU, or you're either going to have to release 360 BTU. Looking at our second example, just a little rearranged. We have joules and we have kilograms, that's fine. Look at the wording here. This is important to know that when they say if you're changing from ice at 0 to water at 0, you're once again just at this flat line. Okay, Q equals LFM, but this time I'm solving for LF, that's fine. You can rearrange beforehand. I'm just going to do it after. Equals our unknown LF times the mass, which is 4 pounds. If you want to isolate that variable, you divide by what's stuck in front of it, and you're going to get 335,000 equals LF. And the units will be joules per kilogram. Check if you're right, go back to the table. I see 3.35 times 10 to the 5. A little bit of scientific notation. So if I take that decimal, move it over 5 points, 1, 2, 3, 4, 5. I feel like I did too much there. Nope, fill in the zeros. There's the same number. Let's build on a little bit. What's going on here? Draw the picture. It shows me you understand. It helps you sort your stuff. Okay, so we have 5 kilograms of ice at 0. So we're starting at 0. And we're going to melt it. So we're going to start with a flat line. That's that change of phase from ice to water. And then we're going to raise the temperature of the water to 50 degrees Celsius. So that's our traditional Cm delta T. So this is what the phase change graph of this would look. It's not the whole thing like that, but because it's only like 2 things happening. We're melting ice and then we're raising the temperature. So I'm going to call this Q1 and I'm going to call this Q2. And in order to find the total heat that you need to absorb, you must add the 2 heat steps. Q1 plus Q2. How am I going to calculate both? Well, Q1 is what we just did. Q1 equals LFM. And for Q2, I'm just going to put it over here. I'm going to go back because we have a change in temperature. We have increasing temperature, so we can use Cm delta T. All right. Starting with Q1, we go to our table. We're looking for joules, so look up the joules in kilogram 1, and we see it's that scientific notation. That's fine. We know how to put that on our calculator. 10 to the 5 multiplied by 5 kilograms. And we get Q1 equals, and I'm just going to write it in expanded form because that's what my calculator barfed out, either or, and that's joules. Q2, go back to your formula sheet. This is like what we did last time. You look up the specific heat for water. This is going to play in too. And you see that's 4190 when you're looking at joules. Our mass is 5 kilograms, and our change in temperature is T2, which was 50, minus T1, which is 0. You do that math, and you end up with a lower number, 1 million, blah, 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 blah. 500 joules. Joules are so crazy. All right, so if I want to know the total heat that is absorbed to make this happen, notice that the heat that's absorbed during the change of phase is actually more than the heat that is absorbed while you're raising the temperature. And that has implications for your industry. And we're going to get 2, 7, 22, 500 joules. So that is the total heat. So when you do these change of phase calculations, you're going to do them in steps. Heat of fusion is only for when you're changing phase between solid and liquid. That's the only place you use heat of fusion, because you use a different heat, the heat of vaporization, LV, V for vaporization, L for latent heat, when you are changing between liquid and gas. So anytime you're at the change between these two phases, you must use vaporization, not fusion. The formula is essentially the same. Instead of using LF, though, you're using LV times the mass or the weight of the substance you're investigating, and that will give you the heat absorbed or released. On your formula sheet, LV is situated at the very end of that big chart on the second page, and it's only given for, once again, a few substances, because that's all we're really going to maybe consider. You don't have an LV, a heat of vaporization, for ice, because ice isn't involved in a liquid gas phase change, but you do have one for steam, which of course will be exactly the same as the one for water. What I'd like you to notice is the difference. So let's just look at the calories per gram. If you are changing water, like from ice to water, the heat of fusion is 80. But if you're changing water to gas, the heat of fusion is 540. So it's quite a bit bigger number. So that tells me that there's going to be a lot more heat flow during the time that I'm switching between liquid and gas. For my first example, I've got exactly the same amount of water, 2.5 pounds, but this time I'm vaporizing it instead of liquefying it. So I just want to note that we had the Q for that phase change, let's say solid to liquid. I want to remind you that that was 360 BTU, so we can compare it to what we get when we go from liquid to gas. All right, Q, when you are vaporizing, heat of vaporization, blah, blah, times the mass. Look it up on the chart, 970 multiplied by 2.5 gives you 2,425 BTU. That is a massive increase over what heat was absorbed to change it from solid to liquid. Second example, now we're doing calories and grams. That's fine. Calorie goes with grams, so as long as the units are in that state, we're good. So we're going to start the formula. Q equals LVM, but this time I have the heat absorbed, and I have the mass, and I'm looking for the heat of vaporization, LV. So I'm going to divide both sides by 250 to isolate that variable, and I'm going to get 540 calories per gram for the heat of vaporization. If you check your formula sheet, that's exactly what it says. So here we can draw it all together. I've used metric just because 0 and 100 are easy for me. So you'll notice that it's kind of hard to see because they're a little fuzzy, but each heat step has been given a number. So here we have Q1, Q2, Q3, Q4, and Q5. So what people really want to do, if I give them something that says I changed from ice at minus 20 to steam at 120 degrees, they try and use one formula, C M delta T, with a change from minus 20 to 120. And that is not what you do. There's a reason this is the last topic, because it's the most complicated. So whenever you are in a phase, so if you are ice, you use the formula Q equals C M delta T. Now notice the C changes depending on the phase. The specific heat is different for each phase of water. So you can't just use 1 or 4190 or whatever, for C. You can only use that for water. You have to go back to the chart. So back on our formula sheet, if we look at water, specific heat is 1 or 4190, depending on whether it's joules or not. When you're down at ice, specific heat is only 0.51, totally different, or 2100. And when you are at steam, the specific heat is 0.48 or 2000. So that's something you have to watch out for. So just filling in these formulas, I said Q1 was going to be the specific heat of ice multiplied by mass multiplied by the change in temperature. Where I'm going to write the rest of this really crowded in here. Q2, which is when we are changing from ice to water, is just going to be LFM. Q3 is when we're going from water at 0 up to water at 100 degrees Celsius, is going to be C of water, specific heat of water, times the mass times the change in temperature. If you go all the way through the phase, it's going to be 100 degrees. Q4 is taking water and making it steam at 100 degrees. Heat of vaporization multiplied by the mass. Q5 is increasing heat in the steam phase. Specific heat of steam multiplied by the mass multiplied by the change in temperature. And the change in temperature for that last phase will be, your finishing temperature minus 100, your starting temperature. So watch out there. That's another common mistake. This is 100% the type of question you're going to get. kcal of heat to change 3.5 kilograms of steam starting at 1. So we're starting with steam at 120 and we're going all the way down to ice at negative 15. So draw the picture. Temperature versus heat. We're going to start at steam. So our starting temperature is going to be 120. And we're going to go down for a little while. This is just a sketch. And then we're going to change the steam into water. Temperature doesn't change, but heat is still added. That's happening at 100 degrees. Woo! Then we're going to go down. Whoa. I can't draw. And take water at 100 and cool it down to 0 degrees Celsius. When we hit 0, we're going to take the water and we're going to change it all to ice. No change in temperature. Then finally, not to scale this bad Larry of a graph, we are going to cool the ice from 0 to negative 15. So from start to finish. So we have how many phases? 1, 2, or how many steps, I should say, not phases. We have 3 phases, but 4 heat steps. Okay, so setting up. I love to see a graph like this, and then I like it broken down. Tell me what you're going to do. So the first step is going to be C of steam, M times the change in temperature. Let's fill it in. Okay, look this up. The specific heat is 0.48. Our mass is going to be the same in every single step, 3.5. Our change in temperature, so I'll stick with making this negative. So we started at 120, we ended at 100, so T2 is 100 minus 120. If you do that math, you will get negative 33.6 kcal. And that's put that point in, and that negative is just telling us that the temperature is dropping. So when you figure out Q2, you can automatically assign it a negative or just assign it, like when you were going and changing phase, you're not going to go up and down. You're just going to continue with the same sign. So if you use the negatives, make sure, even though you're changing phase and temperature isn't changing, you use a negative for that heat, signifying heat being released. Okay, step 2, right here. We're flat, we're changing from steam to water. We use the heat of vaporization and the mass. 540 multiplied by 3.5 is going to give me 1890 BTU, kilocalories, and I'm going to make that negative. Q3, we're going to run out of room. C, specific heat of water, times the mass, times the change in temperature. Well, this one's nice. It's 1 for a specific heat. The mass is 3.5, and the change in temperature is going to be 0 minus 100. And then that's going to give me, I'm just trying to fit it all in, 350 kcal. Woo. Q4, Q5 might be at the top. We are changing from water to ice at 0 degrees Celsius, so we must use the heat of fusion formula, LFM. Go to your formula sheet, get the 80 for LF. The mass is still 3.5. 280 kilocalories. And we're going to fit Q5 right over here. And Q5 is when we are cooling in the ice state, so we use the specific heat of ice times the mass times a change in temperature. Oops, and I forgot to make both of these negative. Q3, Q4, make them negative. All right, specific heat of ice is 0.51 for kcal kilograms, and we are going to do 3.5, and our change in temperature is going to be starting at 0, going to minus 15, so minus 15 minus 0. That will give us negative 267.75. So just to kind of circle the numbers that are going to go into my total heat calculation, Q1, Q2, Q3, Q4, and Q5. So up at the top, the total heat is equal to negative 33.6 minus 1890 minus 350 minus 280. This is where you want to show me your work in case something goes south. Check that you have 5 numbers. And we get negative 2821.35 kilocalories. So if we take 120 degrees Celsius steam and cool it down to ice at negative 15, we are going to release this amount of heat. And notice where we're going to release most of it. Such a bigger number. When we are changing phase between gas and liquid, we have massive heat dump or heat absorption. We'll do an example with another substance in class, and we'll do an example in imperial in class, because we definitely want to be able to do these at, with our Fahrenheit scales as well. And we're going to look at some imperial here, because it's really important to be able to set this up correctly, because not all phase change calculations that I'm going to give you are going to involve 5 heat steps. You're not necessarily going to go at solid ice at a lower temperature than 0 all the way up to steam at a higher temperature than the boiling point. So here we are. So 32, of course, is when we freeze in Fahrenheit, and 212 is when we boil. So just knowing that. So we're going to sketch a graph. So for number 1, temperature versus heat, what are we starting at? We're starting at ice at 32 degrees Fahrenheit at the melting point. So we start with a flat line. And then we go all the way up to the boiling point of water, but we don't change it to steam. So there's only 2 steps in the heat total for situation 1. Looking at situation 2. Same thing. And I guess I could have labeled 32 and 212 there. Okay, so let's put 32 and 212 on this one as well. So number 2, we're starting at water at 32 degrees Fahrenheit, and we're changing to steam at 212. Okay, so we don't have any ice at 32, so we start with an increase in temperature, right? Water at 0 or 32 goes up to the boiling point. Do we have another step? Yeah, because right here at this point we're at water at 212 degrees Fahrenheit. So we want to change it to steam. That's a phase change. That's a flat line. this is what the graph for the situation number 2 looks like. One more, number 3, same, T versus Q. All right, so we're starting with 5 pounds of ice at 30, just below the melting point. So I'm not going to put the temperatures on because it'll be too crazy. So we do a little up a blip, and then we're going to go all the way to steam. Okay, so we are, in this case, going to change the phase. If we're going all the way to steam, we know that we have the entire phase of water. We know that we change the phase at 212, and then we just have a little blip of a rise at the end. So this one is 5 steps, and you will have 5 numbers that you have to add together. But situation 1 and 2, you're only going to have 2 steps. Here you will use the formula LFM, and here you will use Cm delta T with the specific heat of water. Here you'll use Cm delta T and LVM. And in number 3, you're just going to use everything you got. So this one's definitely a tricky one, but if you got it, you are golden.